Welcome. In this video, I'm going to talk about structural isomers. And structural isomers is when there's more than two possible ways to draw a structure from the molecular formula given. So structural isomers start occurring as the carbon stem grows because suddenly there's more than one possible structure from just looking at the molecular formula, which is why the condensed molecular formula is so important and helpful. So butane is the first carbon chain, a string of four, where instead of just putting all four carbons in a straight chain, you could actually have one carbon branch off the middle. So you'll see the difference in the diagram down on the left and the right. The one on the left is called butane because it's got four carbons in a straight chain, but the one on the right is now called methylpropane or 2-methylpropane to let you know that the longest backbone is just 3 carbons, or the propyl group, and then there's also a methyl group branched off it for a total of 4 carbons. So compounds with the same molecular formula but different arrangement of atoms are called isomers or structural isomers, and each isomer has distinct chemical and physical properties. On the previous slide, you maybe noticed that the butane, the straight chain version, has a lower boiling point than the branch version. So even though they may be very similar, they're not considered the same chemical. So they have different structural formulas and they have different names both. And the longer the carbon chain gets, the greater the number of possible isomers. And in fact, that increases exponentially from butane with 1 to pentane with 3 to hexane with 5 and heptane 9, octane 18, and so on. Branch chain isomers tend to have lower intermolecular forces, so lower boiling points. And the reason why is because the branches prevent the isomers or the molecules from having too much contact or getting close enough to develop those temporary dipoles. So think of it like noodles. If you have a shell noodle, it doesn't get tangled up very much, but if you have, some of those short spiral noodles, they maybe get tangled up a little more, and when you have the really long spaghetti noodles, that's when they really make contact and tangle with one another. So here's an example of a structural isomer, and it says draw 2,2-dimethylpropane and write its condensed structural formula. So let me scroll down here a little bit. So the 2,2-dimethylpropane lets me know there's 3 carbon in the longest backbone. There's my propane. And the 2,2-dimethyl lets me know there's a methyl group coming off, 2 methyl groups coming off the second carbon. So once I fill in all my hydrogens, this is what my structure looks like. So how do I write this condensed structural formula? What I would write is CH3, and then I'd write C to show there's the center carbon, and then parentheses I'd put CH3 2, so it's clear that those are branched off, and then finally CH3 again. Or I could write CH3, C, and then put CH3, 3 here. Either condensed structural formula would give you the idea that this is the only possible structure that we're intending. So some structural isomers that have been significant in the world of chemistry include tetraethyl lead, which was added to gas to make the gasoline perform better. And if you think about tetraethyl lead, it would be a PB, and then it's got a CH2CH3 group here, and then a CH2CH3 group here, and a CH2CH3 group here, and finally a CH2CH3 group here. So 4 branches around this lead. And it resulted in high levels of lead ending up in our air and soil, especially near freeways. In fact, 35W running through Minneapolis still has elevated levels of lead in the soil because of all the leaded gasoline that was used. So it turned out to be a bad plan. We now know we could just use branch chain isomers in the octane and the other alkanes that are in gasoline and get the same smoother burning engines. So that's what we use now. When you see high octane gasoline, what we're talking about is gasoline with more branched isomers. Ironically, it was a fellow named Thomas Midgley who came up with the leaded gasoline idea, and he's also the guy who came up with using CFCs for aerosols. And you may or may not be old enough to realize that CFCs are what created the ozone hole. And ironically, he died at age 55 before realizing the damage his two big inventions, his chemicals, had caused. And he was strangled by another invention of his, which is a series of ropes and pulleys to help him get out of bed after losing the use of his legs due to polio. So the guy was just kind of a disaster from get to go. So let's look at some structural isomers in different families. Structural isomers in alkanes are going to be limited by the length of the carbon stem. In alkenes, isomers result from branching the carbon stem, but they can also result from the position of the functional group, and that's true for several families other than the alkanes. So butene has two straight chain versions possible. You could have the carbon double bond between 1 and 2, or you could have it between 2 and 3. So we either call it 1-butene or 2-butene to let you know where that's at. So for families other than the alkanes, you have to consider isomers from both the stem length and the functional group placement. And in fact, some isomers actually result from being from two different families. For example, C2H6O could represent an alcohol or an ether. And this is where the condensed structural formula comes in handy, because if it was the alcohol, we would tend to write it as C2H5OH, C2H5OH. And then it would be clear when I drew it that I intended it to be ethanol, like so. But if it was methoxymethane, then the condensed structural formula would be CH3OCH3 to let us know that the oxygen is single bonded between the two carbons, or the two methyl groups, and it would have a full structural formula like so. So what are the trends? What are the change in physical properties when you have these isomers? Well, one trait of a homologous series or a family is the gradation or increase in physical properties. And there's two parts of an organic molecule that determine these trends: the length of the stem and the functional group. So boiling point generally increases as the backbone increases in length. So this means lower or shorter members will tend to be gases, and the higher or longer members will trend from being liquids to solids. But branching is going to decrease the boiling point because, as I mentioned earlier, it makes it harder for the neighbors to be near enough to develop temporary dipoles. You just can't get as much as surface area in contact with the neighbors. So it's similar to trying to bundle up and carry wood with lots of branches versus carrying pieces of wood that have had the branches cut off or removed from them. Volatility trends very much mirror the boiling point, because volatility is how easily a substance changes to a gas by boiling or evaporation. So a longer carbon backbone will increase intermolecular forces and decrease volatility. So the functional group will have a significant impact on volatility, whether it's polar or nonpolar, with more polar functional groups decreasing volatility and less polar or nonpolar groups increasing volatility. But it also will depend on the length, with length decreasing the volatility. So generally the most to least volatile families based only on polarity are alkanes, being totally nonpolar, or the least polar. Halogenoalkanes have just a slight polarity because of the halogen on there. So a slight dipole-dipole interaction on the halogenoalkane. Aldehydes also have some polarity, so they would be next. Ketones, usually slightly greater than the aldehyde because it's in the center of the molecule instead of on one end. Then alcohols with a hydrogen bond, and carboxylic acids with both a hydrogen bond and double bonded oxygen for a second polar bond. So that tends to be the increasing boiling points, decreasing volatility, and increasing molecular strength. Last trend to look at, and your book didn't mention this one, but I want to bring it up because I'm guessing it may show up in some of the questions that they'll expect you to make this extension, is the solubility in water trends. Remember, water is a highly polar substance. So functional groups that are polar are going to tend to make that particular compound at least somewhat soluble in water. But the carbon backbones are nonpolar, and so they're going to decrease the solubility in water. So the longer the carbon backbone, the less solubility it has in water. But the more polar the functional group, the more the polarity will increase, especially if it has a hydrogen bond in its functional group. So groups that are highly soluble in water are the carboxylic acids, have the greatest solubility because it has the hydrogen bond and a polar bond in the O double bonded to the carbon. Alcohols have fairly good solubility with the hydrogen bond. And then aldehydes and ketones tend to have some solubility because they at least have one polar bond. And then as we look at the other groups, the hydrocarbons, the arenes, we don't see much solubility at all among those groups.